proof. Suppose lambda is an eigenvalue of A, which is self-adjoint, with eigenvector V. Now, what does that mean? That means A times V is equal to what? Lambda being an eigenvalue for the eigenvector V means AV is same as? AV is same as? If lambda is an eigenvalue with eigenvector V, this means AV is same as? I'm just asking you the definition for the inner product. I'm just asking you for the definition of the eigenvalue and eigenvector. Yeah.
Lambda V?
Lambda V, yeah, of course. Good. That's what eigenvectors, eigenvalues mean, right? Okay. So if lambda is an eigenvalue of A with eigenvector V, it just means AV is lambda V. And then we can just work with this. Oh, by the way, eigenvectors cannot be zero vectors. That's another condition. Right? So now let's carry on the calculation. So this time we're going to use the Hermitian inner product. Okay? So I'm going to say that A V and then V is going to be equal to lambda V which is same as lambda times VV, which is V norm squared. But then, because this A is self-adjoint, you can use the adjoint of A to move to the other side. Okay? So remember what adjoint was? I erased the definition, but adjoint of matrix A is what? When you can move from one to the other. Okay? So I say AUV is equal to U adjoint AV. So for a matrix, for any matrix, you can calculate its adjoint. We even found the formula for it, right? For the real case, it's just simply transpose of A. That's the adjoint, right? For the complex case, it's conjugate and then transpose, right? So you can always move a matrix to the other side by taking its adjoint. But what is the adjoint of A?
B.
No. There's no V here.
A.
A is self-adjoint, so adjoint of A is itself. That's what self-adjoint means. So this simply means you have VAV. Okay. But what is AV? Lambda V. And now we use another property that says, we say that the Hermitian inner product is sesquilinear, which means that if you have a constant here, that goes outside not as lambda itself, but as lambda bar. Now this may look strange to you, but it's kind of obvious because in my mind, what is the inner product? It's really V transpose and lambda V bar, right? That's what Hermitian inner products look like, right? So what happens if I pull this in front? It's lambda bar V transpose V bar, right? And what is this? This is V inner product with itself. So of course these two should be the same. Okay? So it looks strange if you write it like that, but if you have this understanding, it's kind of obvious. Okay. So that's what you have, which is lambda bar norm of v squared. So what did we just prove? We proved that lambda times norm of v squared is the same as lambda bar times norm of v squared. And because v is a non-zero vector, norm squared is non-zero, so I can divide both sides by this and get lambda equals to lambda bar. What is that? What complex number is same as its conjugate? Well, 0 and 1, or it could be any real number. Yeah. See, a plus bi, what's the complex conjugate? It's a minus bi, right? But then if a number is same as its complex conjugate, what does that mean? B has to be 0. If b is 0, then it must be a real number. So it's kind of a given. So this implies that lambda is real. Now this even has far-reaching consequences as quantum mechanics. So if you go to quantum mechanics, you have something called observables, and observables are linear operators which are Hermitian. Okay? And because of this property, when you observe something in quantum mechanics, you end up observing the eigenvalues. Okay? You won't understand what I mean, but it's just there. Okay, so one thing that you end up getting is that because you have Hermitian matrices or Hermitian operators, and those are observables, and the quantity that you get to extract from that ends up being real, and this actually proves it. So it's kind of nice. So, as I said, linear algebra pops up everywhere. Right now you'll be learning and not really see the consequences, but as you go to more graduate math, you're going to be amazed by how many far-reaching consequences it has. Okay? So this theorem actually happens to be quite important. That's why I'm asking everyone to know the proof. Okay? The proof is simply being able to move A to the other side and say adjoint of A is same as A. But then if you use the fact that AV is equal to lambda V, suddenly you have the eigenvalue same as its conjugate, which means lambda must be real.